Welcome to a series of videos entitled From the Ancient Greeks to Isaac Newton, Early Astronomers and the Birth of Science. Lecture 1, The Ancient Greeks. We will see the influence of society and culture on scientific progress. We will see evidence of the synergy between advances in mathematics and advances in the physical sciences. That is to say, not only do the two parallel one another, but it also happens that one often motivates the other. Finally, I will make the case that the history of astronomy is the quintessence of the history of science, at least up until the scientific revolution. I made a careful search to find the right word here. Why did I choose quintessence? Let's consider its three definitions. First of all, the word originally referred to the fifth and highest element in ancient and medieval philosophy that permeates all nature and is the substance composing the celestial bodies. In the context of definition number 1, the ancients had another word for quintessence. The ether. The other two definitions illuminate the relationship between astronomy and science up until the time of Newton. Number 2, the essence of a thing in its purest and most concentrated form. Number 3, the most typical example or representative. With these three themes in the backs of our minds, let's proceed by asking some basic questions. First of all, what is science? I'm going to attempt a brief definition. As we go forward, let's remember these words of Einstein's. One thing I have learned in a long life, that all our science measured against reality is primitive and childlike, and yet it is the most precious thing we have. Here's a starting point. Science is knowledge gained through rigorous and ongoing application of the scientific method. Of course, this statement begs the question, what is the scientific method? The scientific method begins with making careful observations of events in the physical world. Richard Feynman, who won a Nobel Prize in physics while earning a reputation as both a genius and a mischief maker at Caltech, said, "I learned then what science was about. It was patience. If you looked and you watched and you paid attention, you got a great reward from it, although possibly not every time." The next step is to take these careful observations and document regularities or recurring patterns over time. The next big step involves formulating a testable hypothesis that postulates a fundamental principle governing those regularities. And it's important to note here that explanations based on supernatural causes are not allowed. Next, one tests the hypothesis. That is, you make a prediction and you put it to the test. This is where things start to get a little trickier. We will see how the ancient Greeks understood the importance of the first two steps, and we're starting to employ step 3, but we won't see a sophisticated approach to testing a hypothesis until we get to the scientific revolution. In truth, the process never really stops, but I will put in a fifth step a final step, perhaps, by simply stating that one needs to observe the results of the test, reformulate the hypothesis as necessary, and then continue testing. The next question is, why does science begin with astronomy? Well, one big reason is that events in the heavens tend to recur with striking regularity. Accurate predictions are possible. Of course, they're only possible if careful observations are made and recorded over extended periods of time. By comparison, events on Earth often appear random and chaotic. Change is a constant. Regularities do occur, but with frequent exceptions and variations. There is at least one observation that can be made on Earth that suggests a highly predictable natural phenomenon. This observation will become very important later on and was of great importance to Isaac Newton. The observation: what goes up must come down. So the next question is, why begin with the Greeks? Well, history teaches us that the Greeks had a preeminent role in establishing astronomy as a science. However, we sometimes have to be careful about what history teaches us. The historical record for this time period is scanty and fragmentary. Also, we can safely assume that it was subject to bias, as it always is. The fact is, Greeks were not the first astronomers. Their predecessors in Babylonia and Egypt recorded large volumes of careful observations that enabled them to make predictions of celestial events with ever-increasing accuracy. The ancient Greeks themselves understood that there was much to learn from the Babylonians and the Egyptians, and the fragmentary biographical material available to us from that era suggests that many of the early Greek astronomers, mathematicians, and philosophers, including the legendary Pythagoras, traveled and studied in Babylonia, Egypt, or both. Nevertheless, Carl Sagan, in his book Cosmos, along with other authorities on the history of science, credit the ancient Greeks for giving birth to science because they aimed to explain the world around them without reference to mythology or supernatural forces. To understand how this trend might have come about, let's back up a bit. Ancient Egypt and Babylonia were highly structured, hierarchical societies with a strong central authority and very limited social mobility. Social order was believed to be ordained by the gods. At the top of the pyramid, so to speak, were the kings and pharaohs. The Babylonian kings derived their right to rule based on divine appointment by Babylon's patron deity Marduk, and through consecration by the city's priests. Pharaohs were actually considered themselves to be divine beings, and served as intermediaries between the gods and humans. Religion may have served many purposes, but for these rulers, its most important role was to validate and maintain their authority. Priests were members of an elite upper class, and their power and status depended on serving and supporting the ruler, and on maintaining religious conformity. Astronomy was closely linked to religion, and because religion was so important in maintaining the status quo, there was every incentive to interpret celestial phenomena in religious terms, and no incentive to interpret them in terms of natural causes. Next on the list come the scribes, the purveyors of written records. They served at the pleasure of the priests and the ruler. One can easily imagine that no one in this select group had any incentive to share their learning and knowledge with the lower classes. Finally, we have the common people. In this setting, knowledge and learning were proprietary. The situation tended strongly towards stifling a spirit of free inquiry and critical thinking. For these reasons, it seems fair to say that science did not begin with the Babylonians or the Egyptians. Nevertheless, early historians might have given the Babylonians or the Egyptians more credit for their accomplishments in astronomy, except that for a long time the historical record of their achievements was virtually non-existent. As it stands now, that record remains highly fragmentary and does not lend itself easily to constructing a coherent narrative. Why is the record so fragmentary? Why is the record of the Greeks' accomplishments sufficiently rich to allow for a coherent narrative? With all these questions in mind, let's turn our attention to the Greeks. The birth of science narrative traditionally begins with Thales of Miletus, who arrived on the scene around 600 BC. Miletus was a prosperous Greek colony on the west coast of Turkey. It had become a maritime power a couple of centuries before the peak of Athens' power. Aristotle viewed Thales as the first philosopher in the Greek tradition, and by that he meant the first natural philosopher, that is, a thinker who does not rely on myths or religion to explain natural phenomena. Thales came up with a cosmology based on the foundational principle that ultimately everything is made of, or originates from, water. As there was no way to test this hypothesis at the time, we should say that Thales was engaging here in speculation, not science. Nevertheless, his speculation represents an attempt to avoid any reference to Greek mythology in explaining the origin of the physical world. Thales' reputation was bolstered by his prediction of the solar eclipse that occurred in the spring of 585 BC. Now, if you are a bit surprised to hear about ancient Greeks living on the west coast of what is now Turkey, remember that ancient Greece had a flourishing seafaring culture. They established colonies and extensive trade networks all around the Mediterranean and Black Sea. In fact, there were several important Greek cities along this particular coastal region, which was known as Ionia. Miletus was part of the powerful Ionian League, made up of these city-states. So Thales wasn't exploring natural philosophy out in the backwoods. He was in the midst of a thriving center of commerce. As another case in point, consider the legendary Pythagoras, who was about 50 years younger than Thales. He was born on the island of Samos, just off the Ionian coast and across a narrow channel from Miletus. During Pythagoras' formative years, Samos was a thriving cultural hub and trading center. The Pythagorean theorem was known and used by the Babylonians and the Indians centuries before Pythagoras, but he may have been the first to introduce it to the Greeks. Then, around the age of 40, for reasons that aren't entirely clear, Pythagoras pulled up stakes and moved to the Greek colony of Croton in what is now southern Italy, where he established a scholastic community of followers. So, with this in mind, we can start to imagine the Greeks traveling around the Mediterranean, sharing ideas, spreading ideas, and even establishing schools. We can make a list of conditions that promoted a flourishing intellectual culture among the Ionians. First of all, the Greeks had the first true alphabet. It was adapted from the Phoenicians, and a brand new feature was added: vowels. Reading and writing now became easier to learn, and literacy increased. There was a lack of any central authority. Greek city-states were relatively independent and isolated due to the rugged coastal terrain. It would be very difficult for a single political entity to dominate an entire region and enforce conformity to a religious ideology or social hierarchy. Indeed, Ionians were known for their love of democracy. The Ionians were prosperous, and their prosperity was based on a free market economy and extensive trade networks. These networks included Mesopotamia and Egypt. These networks facilitated not only exchange of goods, but also exchange of ideas. Economic competition promotes innovation and education. The Ionian League was just a loose confederation. In truth, these city-states were in competition with each other. As Jared Diamond emphasized in his book Guns, Germs, and Steel, economic competition in this context promotes innovation and education. Now, astronomy was of immense practical importance with regard to navigation, and thus to maritime trade, the basis of their economic power. Altogether, these conditions strongly tend to promote free inquiry and critical thinking. Knowledge becomes open source rather than proprietary. Then, several centuries after Thales, this fellow comes along. Alexander the Great. When he was young, his father, King Philip of Macedonia, hired a tutor for his son. The tutor's name was Aristotle. Under the tutelage of Aristotle, Alexander developed a great respect and love for Greek intellectual culture. He also developed a passion for war and conquest, and in a relatively short amount of time he established the largest empire that the world had ever seen. Part of his goal was to spread Greek culture throughout the known world. So off he goes, leading his army through Asia Minor down into Egypt, which he quickly conquers. He establishes a new city there, which he names after himself. Alexandria will quickly become the most important center of learning in the ancient world. The Greek conquerors will build the famous Library of Alexandria, and scholars from all over will come to study its collection of ancient texts. Alexander then takes his army east and conquers the Persian Empire. Now the Persians had conquered the Babylonians, but they allowed the Babylonian priests to preserve their scientific and mathematical texts. And when Alexander marches into Babylon, he wants to make all those texts available to Greek scholars. There's just one little problem. They are written in cuneiform on clay tablets. So Alexander commands the Babylonian priests and the Greek scholars to work together to translate all that accumulated ancient knowledge into Greek. So let's go back to the question I posed earlier. Alexander clearly valued the scientific and mathematical contributions of the ancient Babylonians. Nevertheless, we are probably justified in accepting the opinion of Carl Sagan and others that the Greek tradition of natural philosophy represented a true paradigm shift. At the same time, we might want to remember the caveat offered by Winston Churchill. History is written by the victors. Under Alexander, the Greeks were victorious in conquering Persia and Egypt, and for several centuries thereafter, Greek was the lingua franca of the Eastern Mediterranean, among scholars and the general public alike. Meanwhile, the use of cuneiform soon died out, and the vast majority of these original Babylonian clay tablets were lost to history. The ancient language of the Egyptians and their scholarly texts suffered a similar fate. Clay tablets and papyrus are subject to destruction and decay, and the texts they contain are typically lost unless copies are periodically made. You might wonder about ancient Egyptian hieroglyphics carved in stone. Writing in hieroglyphics was highly labor-intensive and was used mainly in public buildings such as temples, tombs, and monuments. Here it primarily subserved religious narratives, propaganda, and panegyrics. These hieroglyphics, of course, have been preserved at many sites, but they don't tell us much about Egyptian understanding of astronomy. More scholarly works would have typically been written on papyrus, in more simplified and time-saving cursive scripts, the hieratic script and later the demotic script. In contrast, thanks to the conquests of Alexander and later Rome's often reverent approach to preserving Greek culture, Greek manuscripts were copied over the decades and centuries. Much has been lost, but much has survived. With all that historical context in mind, we are now ready to examine some major milestones in the development of Greek astronomy. We begin with a fellow named Anaximander. He was a student of Thales of Miletus, and he came up with the notion of celestial spheres. Now, anyone who has observed the night sky over a period of time would soon conclude that stars generally rise in the east and set in the west, just as the sun and the moon do. But if you looked to the north at night for several hours, as Anaximander did, you would notice something very informative that might be missed by a casual observer. Thanks to modern time-lapse photography, I can show you fairly quickly what it took Anaximander hours to realize. To Anaximander, the North Star appeared to represent the top of the axis around which a giant sphere rotated. He conceived of the stars as fixed points of light on a huge rotating transparent crystalline sphere. The Earth, he thought, was a cylinder floating in infinite space surrounded by the sphere of stars. Those coming after Anaximander realized that the sun, the moon, and the planets did not travel in synchrony with the stars, so they invented separate spheres for each of those bodies. We can appreciate Anaximander's originality by comparing his theory with that of his teacher, Thales. Thales thought the Earth floated in a giant ocean and that there was only one up and one down. For Thales, things fell in one direction only, from high to low. Anaximander thought that whenever you go in any direction away from Earth, you are essentially going up or higher, and that the Earth was therefore the center of the universe. Karl Popper, one of the preeminent 20th century philosophers of science, called Anaximander's idea one of the boldest, most revolutionary, and most portentous ideas in the whole history of human thinking. Here's a question. In what century did someone first have the idea that the Earth revolved around the sun and not the other way around? As far as we know, that is. The answer is the 3rd century BCE. And the credit for this idea goes to Aristarchus of Samos. It would take almost 2,000 years before his view became widely accepted as the correct one. So the Greeks were getting interested in questions like, is the Earth round or flat? How far away is the sun? How big is the Earth? Aristarchus began the search for answers by asking yet another question. Which is closer to us, the sun or the moon? Think about the phases of the moon. Aristarchus would agree with us that the moon revolves around the Earth. If we assume, as Aristarchus did, that what we see of the moon depends on the sunlight it reflects, we can quickly understand that we see a full moon when the Earth is almost directly between the moon and the sun. Similarly, we can deduce that a new moon, that is, the time when the moon is not visible to us, occurs when the moon is more or less directly between the Earth and the sun, and none of the light it reflects can reach us. In fact, of course, when the moon is precisely between us and the sun, we get a solar eclipse. So the moon must be closer to us than the sun. The more interesting question is, how much closer is the moon? Aristarchus realized that when we see a half moon, a line connecting the sun and the moon and another line connecting the moon and the earth must form a right angle. And then he imagined the right triangle shown here. He measured the angle theta by direct observation. He found it to be about 87 degrees. He deduced that the third angle must be 3 degrees. And even though trigonometry had not been invented yet, the Greeks by this time knew enough about right triangles and similar triangles to know that when you know all 3 angles of a triangle, you also know the ratio of any side to any other side. So he figured that the sun, compared with the moon, must be about 19 times farther away from the earth. Aristarchus also understood the concept of the angular diameter of an object at a distance, as this diagram illustrates. Even if you don't know the distance to the moon or its actual diameter, you can measure its angular diameter by direct observation. It turns out that the angular diameter of the moon is about ½ degree, which is also the angular diameter of the sun. That means that if the sun is 19 times farther away than the moon, its linear diameter has to be 19 times as big. This coincidence accounts for why solar eclipses are so spectacular. And because the sun is so far away, its rays hitting the earth are essentially all parallel with one another. Now, if you wanted to challenge me on that statement, you would be justified based on this diagram. Because look, you could draw a ray from the top of the sun, as shown here, and another one from the bottom of the sun, and have them meet at the exact same point on Earth, and clearly these rays are not parallel. But this diagram is not drawn to scale. Remember that the angular difference between any 2 rays can never be more than ½ degree. And this effect is negligible for the experiment that our next Greek astronomer is going to do. Imagine that the Earth is flat and you have 3 cypress trees of the same height at these 3 locations: Macedonia, Athens, and Alexandria. Now you and your 2 assistants measure their shadows on the same day at the same time, let's say noon. Because the sun's rays are all parallel, the lengths of their shadows should all be the same if the Earth is flat. But if the Earth is round, then the shadows should get longer the farther north you are. Now along comes Eratosthenes, mathematician, geographer, astronomer, and chief librarian at the Library of Alexandria. We are still in the 3rd century BCE, shortly after the time of Aristarchus. Now Eratosthenes is very interested in shadows, and he has an idea for an experiment. Now here's a map of Egypt. Eratosthenes is up in Alexandria. He hears the story of a well down in Syene on the southern frontier of Egypt. As it happens, Syene is very near the latitudinal line that we now call the Tropic of Cancer. We'll come back to that in a moment. Here is the well. Most of the year at noon, the sun is more or less to the south, and the well is mostly in shadow. However, at the summer solstice, the first day of our summer and the longest day of the year, the sun at noon is directly overhead in Syene. And the well is filled with sunlight. So, what's going on from our modern viewpoint? Here is a map of the world, and the red dotted line is the Tropic of Cancer. And this illustrates the orbit of the Earth around the Sun. The Earth's axis is tilted so that on the day of the summer solstice, the northern hemisphere is maximally tilted toward the Sun, so that if you are standing somewhere on the Tropic of Cancer, the Sun at noon is directly overhead and you will have no shadow. But if you are standing north of the Tropic of Cancer, you will still have a shadow at noon, which will point north. Now, Eratosthenes does not know all of that, but he does know that when he plants a pole in the earth at Alexandria, it casts a shadow at noon on the day of the summer solstice, pointing north. He has just proven that the earth is round, but he is also now in a position to reason further. He knows L, the height of the pole, and S, the length of the noon shadow. Using the geometry of right triangles, he can determine the angle theta, shown here. He finds that theta is 7 degrees, which is about 1/50th of 360 degrees. In other words, 1/50th of a full circle. He has hired a team to measure the distance between Syene and Alexandria. It is about 5,000 stadia, or about 800 kilometers. Syene is almost directly south of Alexandria. Now here's an important theorem from Euclid's geometry. If you have two parallel lines and a third line that intersects both of them, the so-called alternate interior angles, shown here in green, are equal. Now, assuming that the pole at Alexandria and the well at Syene are both perpendicular to the Earth's surface, Eratosthenes knows that if you extend a line from each of them downward towards the center of the Earth, they will both meet there and form an angle of 7 degrees, based on the rule about alternate interior angles. Now, if that angle is 7 degrees, and if the Earth's circumference is a circle, it is correct to say that the segment of that circumference between Alexandria and Syene is also 7 degrees, or 1/50th of a full circle. The rest is simple math. Remember that he knows that that same arc length between Syene and Alexandria measures out to be 5,000 stadia. So, if 1/50th of a circle equals 5,000 stadia, then the full circle must be 50 times 5,000 stadia, or 250,000 stadia, or about 40,000 kilometers. This was a very accurate estimate. Now, if you want to be nitpicky and you think it through, you might realize that the estimate should be even more accurate if Syene were in fact directly south of Alexandria. However, Syene is actually just a bit north of the Tropic of Cancer, so the sources of error here more or less canceled each other out. The next Greek astronomer that deserves recognition is Hipparchus. He is considered by some to be the greatest astronomer of the ancient world, based on his highly accurate models of the relative motions of the Earth, the Sun, and the Moon. He is also known as the father of trigonometry. In spite of his many accomplishments, Hipparchus was not the most famous astronomer of the ancient world. That title goes to Ptolemy. Ptolemy wrote the Almagest, his treatise on astronomy. Compared to all the other ancient Greek writings on astronomy, the Almagest was by far the most widely read and most frequently copied throughout the ancient world and well into the Middle Ages. But there is a minor problem here for historians of science trying to correctly portray Ptolemy's importance. In the Almagest, Ptolemy borrowed heavily from Hipparchus by his own admission. In some places where Ptolemy tries to improve on Hipparchus, he clearly succeeds. However, in other places, his results have been found to contain significant errors. Later scientists even suspected that he invented much of his data to fit his theories. Isaac Newton called him the most successful fraud in the history of science. Nevertheless, the Ptolemaic model proved to be highly reliable, at least for all practical purposes, in predicting the motions of the planets and the stars. And so his model was accepted as the gold standard until the scientific revolution. Let's pause here, step back, and look at the big picture over time. There are basically two models of the universe. As far as we know, Aristarchus was the first to propose a heliocentric model, but he attracted virtually no followers. The vast majority of ancient Greek authors favored the geocentric model. I mention here the most notable ones: Anaximander, Aristotle, Hipparchus, and Ptolemy. Anaximander was the first to clearly articulate it. Aristotle was not an astronomer, but that did not stop him from weighing in, because that's what he did. He weighed in on just about everything. In the standard geocentric model, the Earth is at the center and does not move or rotate. There are separate spheres for the Moon, the Sun, all 5 known planets, and the fixed stars. They are called the fixed stars because they don't appear to move relative to each other, although we now know that such is actually not the case. There are also spheres for air, fire, and the heavens beyond the stars, but we can safely ignore those. Now, Ptolemy realized from observation that the planets did not travel in simple perfect circles around the Earth, as earlier Greek philosophers would have it, and so he had to fine-tune the model. These deviations from simple perfect circular motion around the Earth stem primarily from the fact that, as we know, but Ptolemy did not, the planets and the Earth actually orbit the Sun. His fine-tuning involved the introduction of epicycles, deferents, and equants in order to account for these deviations. Of these, we will only consider epicycles in our discussions, but before we get to epicycles, we have to introduce some other concepts first. I want to explore with you a somewhat simplified version of the Ptolemaic model and how it works, because in order to understand fully the contributions of the giants of the scientific revolution, it's important to understand what they were challenging and why it was hard to challenge Ptolemy, given that his model worked quite well. In order to understand the discussion that follows, we need to agree on the orientation of the diagrams that we will be looking at. Imagine yourself in outer space looking down on Earth from above the North Pole. For simplicity, imagine that our observer on Earth lives on the equator, and let's ignore the tilt of the Earth's axis. Here we see the Washington Monument and the Transamerican Building, not to scale, which we imagine for simplicity to lie on the equator. Now, if we imagine an observer standing on the equator between the two buildings, anything to the west of the person will be to our right on this diagram, and anything to the east will be on our left. If that person watches a full moon throughout the night, they will, of course, see it rise in the east and set in the west. From our vantage point in outer space, assuming that our geocentric model is correct, we would see the moon revolving clockwise around the Earth. Indeed, from a vantage point in outer space above the North Pole, we would expect to see all celestial bodies revolving clockwise from hour to hour. In the Ptolemaic system, this was known as first motion. It was assumed but otherwise ignored. That is why descriptions of how the model works focus on motions occurring over multiple days, weeks, months, and years. As we go forward, we want to set things up so that we can ignore the 24-hour cycles, or first motion. Imagine this observer at midnight standing at the equator of an Earth that does not have a tilted axis. The constellation Gemini happens to be directly overhead. Gemini is one of the constellations of the zodiac. The other 11 are shown here, forming a great circle around the Earth. They are separated evenly by regular intervals of 30 degrees. The person can infer that the sun is directly beneath their feet, because that is the definition of midnight. That means that the sun is aligned with the constellation Sagittarius. The following midnight, everything looks pretty much the same. So here's this person the following night. Now they understand that in order to detect subtle differences in the rotation rates of different spheres, you have to look at the sky night after night for weeks or months. They also know that you have to note the positions of the heavenly bodies at exactly the same time every night, so that your observations are not affected by their 24-hour cycles or their first motions. As it happens, after about 30 days, it is clear that something interesting is happening. Cancer is now directly overhead at midnight, so the sun must be aligned with Capricorn. The sun has moved 30 degrees counterclockwise in this diagram, or 30 degrees eastward from the perspective of Earth. The sun will continue to move eastward 30 degrees each month until, after a total elapsed time of 12 months, the observer sees Gemini directly overhead at midnight, and the sun is once again aligned with Sagittarius. Now we are ready to add in the planets. Let's start with Mars. Let's say that at midnight Mars is directly overhead in line with Gemini. What do we see after 30 days? After 30 days, Cancer is directly overhead at midnight as expected. Mars is no longer directly overhead, but it is no longer directly in line with Gemini either. It's about halfway in between. It appears to be rotating eastward about 15 degrees per month. What about the other planets known to the ancients? In order to help us understand the motions of the planets relative to the fixed stars and also to each other, it will be informative to add in Jupiter and Saturn to our diagram. Let's start here with Jupiter just to the west of Mars and Saturn just to the west of Jupiter. After 3 months, the Sun has moved 90 degrees eastward, or counterclockwise on this diagram, while Mars has moved about 40 degrees eastward. Jupiter has only moved about 7 degrees eastward, and Saturn starts to trail further behind, moving only 3 degrees eastward. So the rates at which the planets move around the Earth are quite variable, but the general tendency to drift eastward holds for all of them. However, the earliest astronomers, to their surprise and consternation, noticed that every so often one of the planets would start moving in the exact opposite direction, as Mars is doing here, clockwise relative to the fixed stars. For Mars, this goes on for about 10 weeks or so. This change in direction is referred to as retrograde motion. It tends to happen around the time the planet is in opposition, that is, when it is on the opposite side of the Earth from the Sun. To account for this retrograde motion, Ptolemy found it necessary to add in epicycles to the planet's primary circular motion. So here we see the epicycles added in. Relative to the fixed stars, the planets generally move counterclockwise, but every once in a while they execute a little loop-de-loop, according to Ptolemy, and temporarily are observed to travel in the opposite direction. Now for fun, let's see how we can understand the retrograde motion of Mars in a heliocentric model. We're jumping ahead, but it'll be useful to be able to compare the two models. This animated video will simulate the path of Mars, including its retrograde motion. We are looking down from our usual vantage point above the North Pole of Earth. The blue planet is Earth and the red planet is Mars. From this vantage point, they both orbit the Sun in a counterclockwise direction. The pink cone will trace out the path of Mars as seen from Earth against the fixed stars. Think of this video not as a continuous record, but rather as time-lapse photography, showing the relative positions of Earth and Mars at the exact same time each night, night after night, over several months. The retrograde motion will occur after Mars enters that rectangle on the left. The rectangle on the right will show a simultaneous view of Mars from Earth. Recall that the Earth revolves around the Sun at a faster angular velocity compared to Mars. If you observe carefully, you will notice that the apparent retrograde motion occurs just as Earth is catching up to and passing Mars. Thus, the apparent retrograde motion is due to the reversal of the positioning of Earth and Mars relative to the fixed stars as Earth travels past Mars. This effect reflects the more general principle known as the parallax effect. So we can see how the geocentric model and the heliocentric model each have their own unique way of explaining the retrograde motion of planets. One could criticize Ptolemy for not having any real basis for his version, and yet, in fairness to Ptolemy, I want to finish this first video by pointing out that his model does have something of a mathematical basis to it. After all, one of the themes of this video series is that mathematics and scientific advances go hand in hand. So, again, the question is there a mathematical basis for the Ptolemaic model and his epicycles? There are, in fact, geometric figures known as epitrochoids, which, depending on the values of certain parameters in the equations which describe them, can resemble circular orbits containing epicycles. However, the difficulty here would be finding fundamental laws of nature that could explain the basis for the specific values of these parameters in order to account for the particular shape of each planet's orbit. The sort of explanation involving fundamental laws will only become achievable after great efforts by brilliant minds, beginning with a new revolutionary model of our universe. You are now prepared to proceed to Lecture 2, Copernicus and Galileo.